Hello, ladies and gents. Welcome to this webinar focused on simulation-driven design using DesignBuilder optimization. I'm Dave Cocking, and with me today is Andy Tyndale from DesignBuilder. We'll also be joined by Arturo Ordóñez of Sol-Arq from Mexico. Arturo is an architect. He's registered with ISAD in Mexico and has been practicing in a wide variety of sustainable architecture and design projects for the last 26 years. Arturo has master's degrees in bioclimatic architecture and also in air conditioning and energy efficiency in buildings. And he's worked as a professor in architecture at several universities in Mexico, Colombia, Panama, and Spain. He gained his PhD studying the effects of architectural design variables on the energy and environmental performance of office buildings with the Rovira y Virgili. Apologies for anybody in Catalonia if I got the pronunciation incorrect there. University in Tarragona in Spain. After this brief introduction, I'll hand you over to Arturo, and he'll start his presentation by explaining how optimization works, before then showing you how it can be used effectively as part of a simulation-driven design process. Arturo will then show you how he used DesignBuilder's optimization tools to significantly reduce energy consumption and construction cost, whilst maximizing the use of healthy materials in an eco-friendly house project in Spain. That project was actually shortlisted for a prize in the 2018 CIBSE Building Simulation Group's annual competition. The building performance simulation community, and even to some extent national governments, have talked very positively about the benefits of multi-objective optimization for many years now, perhaps even decades. But optimization still seems to have struggled to make the transition from academic research to wide-scale industry use. Just last week, there was an IBIPSA webinar on the future of building performance simulation. And in that, they commented that simulation is not reaching its true potential because of the absence of application know-how in relation to model making and multi-criteria whole system performance assessment. The traditional way of pre-selecting and simulating fixed single design variables such as glazing, shading, construction types, thermal mass and HVAC systems gives you an indicator only of the likely performance of that specific but constrained design. This traditional deterministic approach fails to identify other potentially better performing combinations of design variables. And that really prevents you from utilizing the full benefit of simulation. For a relatively small amount of effort, which involves setting up a range of appropriate glazing, construction, HVAC types, etc., in your model, instead of just one choice for each, you can use the simulation tool to do the heavy lifting and end up with a far higher degree of confidence that your design is at, or at least near, some kind of holistic optimum. The main reason for the slow adoption of optimization by mainstream industry appears to have been the absence of tools that are easy enough to learn and fast enough and robust enough to use to make it commercially viable for mainstream industry firms and practitioners to include optimization in their normal workflow. That's no longer the case. DesignBuilder's proud to have led that charge and to be at the forefront of helping industry tap into the power of design optimization using genetic algorithms coupled to Energy Plus. These tools can really help to reduce both the capital and environmental cost of construction, helping you to deliver buildings that cost less to build, that are more sustainable in terms of their embodied and operational energy, and that are more comfortable and healthy places for occupants to work and live. Arturo's case study will provide a really good example of that. You can submit questions at any point during the webinar via the question box in the control panel. We have allocated time at the end to answer as many questions as we can, so we expect the webinar to last around 45 minutes. It is being recorded, so you can also access the recording later if required. So I'll now hand over to Arturo.
Okay, Andy and Dave, thank you very much for the invitation. I think it's a great opportunity to promote good practices on building energy and environmental analysis. Well, here you can see the content of the presentation. Firstly, we will speak about two subjects that I think are important as backgrounds. Next, we will explain the project requirements and goals. After that, we will describe the workflow of the project, including a brief demonstration of how we use a DesignBuilder optimization module. And finally, we will comment on some general conclusions. The first background subject can be explained with the help of the McLean's curve, perhaps known by many of you. It shows that the more developed the project is, the lowest the ability to impact cost and performance, and the higher the cost of the design changes. This graph is frequently used to highlight the convenience of shifting the design efforts to the earliest design stages. In this context, it means that it's very important to start the energy and environmental analysis as soon as possible. In fact, in this project, we started this analysis before the beginning of the design process itself. The second background subject is about computational optimization based on evolutive algorithms, the main analysis method we used in this project. In general, it can be described as an explorative combinatory analysis method inspired by natural evolutive processes, which allow us, for example, to explore a wide range of possible design solutions, even millions of those, to identify the best design solutions, considering even contradictory performance objectives such as energy consumptions and construction costs, and to do those tasks in a much more efficient manner than with other analysis methods. But how it works? The DesignBuilder optimization module implements one of the most known and reliable optimization algorithms. It's totally integrated into the general simulation model, allowing the development of the workflow that you can see in this diagram. It seems to be quite complex, but it will represent an iterative process in which the software intelligently searches the design space for solutions that best meet the design objectives and then focuses further generations on those solutions. It works in the same way that natural evolution or survival of the fittest do. The best thing is that DesignBuilder facilitates the setting of the optimization analysis even for non-expert users. Once an optimization analysis is set up and started, all the process happens automatically behind the scene. Okay, the project is located in Els Pallaresos, in Catalonia, Spain. It's about 100 kilometers from Barcelona and 6 kilometers from Tarragona. The zone has a Mediterranean climate with relatively mild winters and summers. However, the heating and cooling loads can still be significant. In the graphs, you can see the monthly temperature values as well as the annual cooling and heating degree days. For the analysis, we use an early weather data file generated with the software Meteonorm. The file was validated using statistical data corresponding to constant T, the nearest and more similar location with weather measures. It's an important point, as the accuracy of the outputs greatly depends on the accuracy of the weather data file. The land plot has an almost rectangular shape and near 800 square meters. One important feature of the land plot is that it's perfectly orientated toward the south, which is known to be the best orientation in cases like this. For this reason, we didn't include the orientation in the optimization analysis. Regarding the house characteristics, the owners asked for a detached house of around 150 square meters, with the main spaces included in the list that you can see here. They also asked for an architectural plan as simple and functional as possible. In resume, our main goals in this project were to accomplish high energy efficiency, reduced ecological footprint, and low construction costs. All of these using materials that are healthy for occupants. Well, in order to meet the previous goals, we implemented three important approaches. To apply a simulation-driven design from the very beginning, to evaluate many possible design solutions, and to consider consistently the environmental and economic performance of the house. Thus, the project involved four main phases: the optimization analysis, the development of the architectural design, a parametric analysis to fine-tune the project, and the development of some complementary analysis, all this in DesignBuilder. The last two phases were run almost simultaneously. Okay, as previously stated, the optimization analysis allows us to investigate efficiently the performance of many possible design solutions. In this case, the analysis was driven by two objectives: to reduce the carbon emissions associated with energy consumptions and to minimize the initial construction cost or capital cost. In the optimization analysis, we included 7 design variables, each with a specific number of options. We included 7 building forms, all with the same main spaces and the same useful floor area. The 3D model developed in DesignBuilder included the internal distribution of common dwelling spaces, as you can see in the images. Obviously, each form has its own set of geometric parameters, which impact energy and environmental performance. The graph shows the values of 4 of these parameters. For example, the first parameter, the external surface divided by the volume, is also known as the form factor and is related to the building capacity. However, all the models were calibrated to have practically the same useful floor area, variating only the wall and circulation areas. This criterion is essential to compare fairly the performance of different building forms. We included also 11 window to wall radius. This variable affects only the windows in the main spaces. In secondary spaces such as bathroom, for example, the windows are smaller and remain always with the same dimension. Okay, the analysis included 46 construction sets, mainly defined by the combination of two design variables, the thermal mass and the insulation. They are also divided into two groups, one with common Spanish materials and other with components of cellular concrete. It's important to highlight in this case that the cellular concrete was proposed by the owners because it's a material with a low embodied carbon, excellent hygroscopic properties, and null volatile compounds. We also consider 12 glazing options. This option results from combining two design variables, the number of glass panes and the glazing type. And finally, we consider the 4 shading options for the windows on the main spaces. These shading were modeled as overhangs and side finds with different dimensions. The first option implies that there is not shading at all. Okay, as you can calculate, the optimization search space was of around 170,000 solutions. The optimization module of DesignBuilder allowed us to find the optimal solutions, simulating only about 7,000. It means that if you want to find the optimal solutions by means of an exhaustive parametric analysis, simulating all the possible design solutions, you will need more than 1,400 hours of simulation time. That's more than 50 days. With the optimization method, we needed less than 60 hours of simulation time. Okay, now we will do a pause in the presentation to show you how we implemented optimization analysis in DesignBuilder. Okay, here you can see one of the models we used. As you remember, we have 7 different building forms. This model corresponds to the first one. And when you are going to run an optimization analysis, the first thing you have to do is to prepare your model. I mean, the geometric part of the model that you can see here. For example, in this case, you can see that we are modeling every space in the house as a thermal zone. And it is very important because in this case, we are defining, for example, regarding the data of the model, we are defining activity data for every kind of space. For example, the bathrooms, the bedrooms, the circulation areas, the kitchen, every kind of space has its own set of activity data. So you can see this is a detailed model. No? Now, obviously, it's very important also to define properly the site data. No? In this case, for example, we have to link our model, as you know, to a weather climate data file corresponding to the zone where we are working. Also, in this model, you have to define properly, for example, the data related to light, no? To the artificial light. In this case, for example, you can see that we are using a lighting control in order to take into account how are we taking advantage of the use of daylighting, and this is important in our model. You have also to define properly the configuration of your HVAC systems. In this case, you can see we have defined a heating and a cooling system, each with its own COP. And the most important thing, because it's not a normal simulation model, here in this case, as we are optimizing, one very important thing is to define all the data that the optimization model will use. For example, regarding the constructions, we have defined, you can see in this panel, all the templates that will be used in the optimization runs. Obviously, you have to prepare it previously, because if not, the optimization model can't use this data. No? Something similar with glazing, for example, in this case, we have all these templates prepared, so we can use in the optimization model. Okay, once you have your model prepared and ready, you have to define the settings of your optimization analysis. You can go to this icon and you get this dialog. In this part, you can define the characteristic, the setting of your optimization analysis. No? The first tag, for example, in this dialog, allow you to define the objectives. As you can see, here we have selected to minimize the carbon, no? And to minimize the cost. These are both the two optimization objectives that we selected. All these objectives, you can select different objectives from the data provided by DesignBuilder. For example, if I open here you can see all the options provided by DesignBuilder. You can select whatever of these optimization objectives. Okay, in the second tag, you can define constraints. These are some kind of limits for your results. In this case, for example, we defined discomfort hours, no, with a number of 150 hours maximum. So this kind of constraints act as somewhat as an objective also, because the optimization results will be guided also by these constraints. And finally, in this tag, you define the design variables. You can see here, for example, the constructions. I have a design variable that is the construction. If I open, you can see here how we selected 46 options that come from my database. Here you can see all these elements that are checked. Is because these construction templates will be used to define the models in the optimization run. Something similar with the glazing. We have several glazing templates that are selected in this part. You can see here all these elements checked will be used in the optimization analysis. Okay, the same for the facade type and the local shading. But here I want to point out one very important feature in this case. For example, for the constructions and the glazing templates, you can see that I have one target object. It is because the first two variables are defined for the wall building. On the other hand, in the facade type, for example, I have 5 targets. If I open this, you can see here in the target part that I have selected only some of the spaces of the model. It means that, for example, the window size only will change in the spaces I'm selecting here. This is a very important feature because you can target different elements in your model depending on your requirements. Also, for the sharing device, we are selecting the same 5 targets. Okay, here is where you define your optimization settings. Once you have it ready, say OK. The next step is to run a first normal simulation. You have to go to the simulation tab here. And you have to run a normal simulation. This starting simulation is very important also to check that your model is working fine and that everything is okay with it, and you will not have problems in your optimization run. Okay, once you have the results of your starting simulation, then you can go in this screen to the optimization tab here, and then you are in the optimization screen. You can start your analysis. You can do a click here. Then you get this dialog. In this dialog, you can define some parameters for your analysis. It's it's a bit complicated to explain the meaning of each of these parameters, but for most of the analysis, the default data defined by DesignBuilder is okay. Okay, once you define these settings, these parameters, you can start your optimization run. And for this, you can do a click here. Now the optimization is running. In this part, you can see that the software tell you that it is simulating, and in a while we will get some results. Okay, I will be back to the model later to see you some of the results. Now we'll go again to the presentation. Okay, as previously mentioned, each building form was optimized in a separate optimization run. Afterward, the results of all forms were combined using the orange data mining tool in order to generate the graphs shown here. I mean, in this case, each one of the building forms was simulated in a separated way. And I want to show you, just for your convenience, sorry. We use this software. This is Orange data mining tool. In this software, well, previously we prepared one Excel file where we combined all the results of the 7 building forms. Obviously, you have to get this information in a certain format, etc. But once you have it prepared, you can link here in this tool to generate graphs like this. As you can see in this graph, we are showing all the optimization results, the whole optimization results. And here we are plotting the carbon and the cost in the axis. And then we can play, for example, with visualizing and exploring the data. Okay, just you know that you can use this kind of tools to handle your results. I will go back to the presentation. Okay. This first graph shows the full results of the 7 optimization runs, as I told you, identifying each form option with a color. The x-axis indicates the operational carbon emissions, while the y-axis indicates the initial building cost. Thus, in the lower left part of the graph, we can find the design solutions, which simultaneously reduces construction cost and carbon emissions. This other graph is based on the previous one, but only shows the Pareto forms of the 7 forms. It's evident that the first 2 forms show the Pareto, the first 2 forms offer the best performance, with the second one having a slightly better performance. I mean, this the one with the red color. Note that the Pareto front represents the line of solutions that are not surpassed by other design solutions in both performance objectives at the same time. Finally, this graph shows only the Pareto front of the second form, which can be considered the overall best one. It also highlights three favorite solutions with its corresponding design options. Here we selected these three solutions as the most suitable for our design. And you can see here all the data related to this model, for example, the constructions. You can see that in all the cases, we have the construction that are mixing cellular and alveolar concrete. However, we have three different insulation levels from very low in this part is the most economic one, medium, and sorry, the higher insulation level. One important thing here is that, as you can see, the window to wall ratio is almost in all the optimal solutions on 0.25. So it's important, according to the optimization analysis, to keep the size of your windows as small as possible. Okay, the next step is the architectural project. The architectural design was developed from the results of the optimization analysis, but also considering the peculiarities of the topography and, in a more detailed way, the specific requirements of the owners. Regarding the form, we adopted a solution that could be defined as a halfway, since it combines the two most optimal options, as you can see here. It's some kind of combination. And almost all the main spaces in this project are on the ground floor. But the studio forms a mezzanine that communicates with the dining living room by a double high space. You can see it here. Also, as suggested by the optimization analysis, to meet the performance objectives, the overall window to wall ratio in the main spaces was kept at 0.25. This is enough to provide good views for the occupants, and the daylighting analysis that I will explain later showed us that daylighting levels are good. Finally, instead of window shading devices, the project included architectural self-shading in order to reduce the cost. You can see this architectural self-shading in this part of the model, of the plan. Okay, here you can see some internal views of the project, with in this case with the sun entering profusely during the winter season. Okay, the next step, the parametric analysis. It was the third phase, and we carried out a series of parametric simulations intended to verify the performance of the project and further optimize constructions and glazing. It was based on the simulation model that I derived from the architectural design project, as you can see in the image. In total, we simulated 12 solutions, which derive from the matrix of options shown in this figure. You can see here 2 construction options, 3 insulation levels, and 2 glazing options. In this case, to evaluate the design solution, we extended the performance to consider the life cycle cost and carbon. The first performance objective represents the initial cost plus the operational cost during the life cycle of the house. The second one, on the other hand, represents the embodied carbon, which is associated with the construction materials, plus the operational carbon, also during the life cycle of the house. These are the results. The graph shows the life cycle cost with the blue line and the life cycle carbon with the red one. Here is this. Here you can see the cost and the carbon. The cost, as you can see, tends to increase gradually as the constructions are improved in this way, while the solution based only on cellular concrete produce lower carbon. We have this group that is only cellular concrete constructions. So the solution pointed out by the blue arrow has the lowest carbon and an affordable cost. Together with the owners, we finally selected this solution for the project. Complementary analysis. Okay, we use a DesignBuilder to develop some complementary analysis. For example, the project was evaluated to verify the compliance with the requirements of the Spanish Building Technical Code, the CTE. For that, we used the leader exporting tool developed by Aurea Consulting and integrated into DesignBuilder. We found that the project easily complies with the limits of energy demands and consumptions. Furthermore, the project obtained the highest energy certification rating, as you can see in this part. Also, we used a detailed HVAC model of DesignBuilder. We modeled an air conditioning system with an air-to-air heat pump to evaluate our project regarding the passive house standard. According to the results, the heating and sensible cooling loss are below the limits defined by this standard. And finally, since according to the optimization result, we kept a window to wall ratio of 0.25, we wonder if the project has a good daylighting performance. Thus, we developed several analyses with the daylighting module of DesignBuilder. The results indicate that the project will get at least 1 credit of LEED version 4, with 76% of the area meeting the illuminance requirements. Okay, the last phase of this study, we simulated 3 additional models intended to answer the question, okay, finally, how good our final project is. The idea basically was to check how close the performance of our project is to the solutions obtained in the optimization analysis, as well as to compare it with other related benchmarks. Here you can see this is our project, and here you can see the other 3 models. The first one relates to a project previously developed by another architectural office. The second one represents a common project with the kind of architecture commonly seen in this zone. And the third model represents the most optimal possible project according to the results of the optimization analysis. This table shows the characteristics of each model. It's important to consider that we verify that all the models comply with the requirements of the Spanish Building Technical Code. Okay, the results show that our project offers saving of more than 70,000 euros compared to the common project, and more than 32,000 euros compared to the previous one. On the other side, the difference between our projects and the optimal project is quite small. Also, we have a reduction of more than 42 tons of carbon compared to the common project, and more than 60 tons compared to the previous one. Again, the difference between our project and the most optimal possible is very small. So it means that our project, even taking into account the real requirements of the owners and the site, etc., even in this case, we are very, very near to the most optimal possible. As conclusion, we can highlight the huge benefits of simulation-driven design. especially if it's played from the beginning of the project, as well as the great potential of computational optimization as a tool to improve the energy, environmental, and economic performance of buildings. Without a doubt, the optimization model of incorporated in DesignBuilder has been a great step to extend the use of this type of analysis. Finally, it's important to consider that the methodology we explained here can be applied to any project type and size. Thank you very much for your attention.
Hey, thanks, Arturo. That was actually a really interesting presentation. It's very refreshing to see this kind of progressive modelling being used to deliver really good results for commercial clients. I think the results that you showed us that the optimal solution for this project was actually a trade-off between construction cost and operational energy consumption. But you, I think, brought out the really important point that in practice, the theoretical optimum that you get from these kind of analyses often gets traded off against client requirements like aesthetics. And I think that's one of the real beauties of optimization, is that it can keep you focused on those key design objectives, and it helps the client to see the impact of the inevitable trade-offs that happen often later in projects. For anybody viewing, please note that you can access a summary of Arturo's case study on the case studies page of the DesignBuilder website. So we hope that you've seen from today's presentation that the design, sustainability and energy modelling community do now have tools at your disposal that enable you to cost effectively utilise the power of optimisation. Arturo's passive design case study demonstrated that optimisation is now both accessible and viable in an industry context. Optimisation could be included in your workflow to help you and your clients reduce both the capital and environmental cost of construction, whilst increasing the quality of buildings for occupant health and well-being. Thanks again to Arturo for his presentation, and also to you for listening. That's the end of our formal presentation, but we'll stay live for another few minutes to take any questions. There'll be a brief pause now whilst we review the questions already submitted, and we'll start answering them shortly.